Dark matter and dark energy taken together are about 95% of the stuff in the universe. However, they represent much less than 95% of the lectures you can buy from the teaching company. So part of our goal in this set of lectures has been to redress that balance, to really concentrate on that 95%, on the dark matter and the dark energy. When we talked in the last lecture about inflationary cosmology, it's not because inflation gave us directly a theory of dark matter and dark energy. Rather, it relates to the background set of assumptions that we deal with when we start talking about things like dark matter and dark energy. When we are cosmologists working and trying to understand the current universe, the idea that the universe probably underwent a period of inflation at very early times colors how we think about everything else. And when we discover new things about the universe, it colors how we think about inflation. For the obvious example, when we discovered dark energy, it helps show that the prediction of inflation, that the universe was spatially flat, was something that was going to be correct. Likewise, the physics of inflation, with a scalar field, a field that is slowly rolling and changing its energy density only very gradually, has showed up once again in ideas for dark energy. So today we're going to be talking about a different background theory, the theory of string theory. String theory is what a lot of people have in their minds in the background when they're thinking about the fundamental laws of physics, both particle physics, as we know it in the Standard Model and perhaps beyond, and also gravitational physics as understood in general relativity. Like inflation, string theory is a speculation. It's not something that we absolutely know is true, but it's something that has caught on as a very popular speculation. There's a tremendous amount of intellectual effort going on right now trying to relate the ideas of string theory to the things that we observe here in nature. So the idea behind string theory is really extremely simple. It's just the statement that you replace elementary particles with elementary strings. In other words, in the conventional way of looking at things, if you take an electron or a quark or a photon and you zoom in on it with the most powerful microscope you can imagine, they still remain point-like. They don't have any extent in any direction. They're just a fundamental geometric point. So string theory says that's not right. Instead, these particles that we think are particles are actually little loops of string. That is to say, they have one dimension of extent that takes the shape of a circle, and that circle is vibrating just a little bit. We don't know what the strings are made of. It's not even a sensible question to ask. They're made of the stuff that strings are made of. But the idea is that different ways you can vibrate a string correspond to all the different particles that we see. This theory has caught on for many reasons, primarily because it's a promising theory of quantum gravity, as we will discuss, but also it's prospectively a theory of everything. And everything includes dark matter and dark energy. So what we're going to be talking about is the possible ways that the ideas behind string theory can influence our conception of dark matter and dark energy. As far as dark matter is concerned, there are sadly more than one possibility for the way that string theory could give us a candidate dark matter particle. It's consistent with our ideas of supersymmetry and WIMPs, also with our ideas of axions and perhaps even neutrinos. For dark energy, it's a trickier situation. You can get quintessence out of string theory, but it's not very natural. The very intriguing suggestion is that string theory can offer an explanation for the size of the vacuum energy. That's the good news. The bad news is that the explanation involves 10 to the 500 different regions of space-time which we don't see. So we're going to evaluate that suggestion very critically in the next lecture. In this lecture, we're going to try to set up what string theory is, why we're motivated about it, and what the current state of the art is, and trying to connect it to other things about the world. So the reason why we care about string theory is mostly because it's a prospective theory of quantized gravity. One of the themes that we've had all throughout these lectures is that in physics, all the theories we have and all the data that we have to be tied together. You don't have a separate theory for every phenomenon. You have the smallest possible set of theories that can explain the greatest possible set of phenomena. In particular, you know that if your theories are really going to be right simultaneously, then they need to be consistent with each other. If you have two ideas that work really well in their respective domains of validity, but are fundamentally incompatible with each other, then you know that something has to give. You know that either one of them is wrong and needs to be replaced, or you need to find a third theory that takes both of them into account and reduces to the two different examples and two different limits. So this is a way that scientists can make progress even in the absence of direct, explicit, and specific experimental data. Sometimes you know your theory is wrong because you do an experiment and it contradicts the theory. That's an easy way to know that there's something that needs to be fixed about how you're thinking about things. But sometimes you know your theory is wrong even though it is consistent with all the data you have. And that is a situation we find ourselves in right now. It's not the first time. In the past this has worked. For example, in 1900, we had the theory of electromagnetism as put together by Maxwell with Maxwell's equations. We also had the theory of classical mechanics as put together by Isaac Newton. But these two theories were not quite compatible. They had different sets of symmetries. They gave different answers to what would happen if you observe the same set of phenomena in two different reference frames. So just by thinking how to reconcile these two points of view, Einstein was able to come up with this special theory of relativity. Almost immediately after inventing the special theory of relativity, he realized that this new theory was incompatible with Newton's theory of gravity. He would once again have to reconcile these two things. There was some experimental guidance. He knew about the orbit of Mercury being anomalous, but nevertheless his primary goal was to find a single framework which could reduce in the right circumstances both to Newtonian gravity and to special relativity. He ended up coming up with general relativity. So now we have a giant looming incompatibility in the fundamental laws of physics. As far as we know, every experiment we've ever done, here on Earth at least, can be explained by one of two theories. The general theory of relativity, Einstein's theory of curved space-time as gravity, or the standard model of particle physics, a set of fields and their interactions governed overall by the rules of quantum mechanics and quantum field theory. The problem is, general relativity is not a quantum field theory. It's a classical field theory. Even though in some sense general relativity replaced ideas of space-time that we got from Isaac Newton, in philosophy general relativity is very Newtonian. It says there is a state of the universe, there are equations that govern the evolution of that state, and we can observe that state in any way we like, in principle to arbitrary precision. The rules of quantum mechanics say something very different. They say that we can't observe everything about a system. There is a wave function. A wave function tells us what the system is really like, but when we observe it, we don't observe the wave function directly. There are certain observable features of it, and when we look at something, the observable thing we get depends on the amplitude of the wave function. What the wave function is really telling us is the probability for getting certain results when we actually observe something. So we want to reconcile these two theories. It can't be the case that general relativity is correct and quantum mechanics is correct. If general relativity is correct, then the source of gravity is energy and momentum, but quantum mechanics is telling us that energy and momentum are just things we observe. They're not the fundamental things that are. In other words, we could imagine, at least hypothetically, a quantum mechanical situation in which you had a gravitating body, and the wave function of the gravitating body said there's a 50% chance that it's over here, and there's a 50% chance that it's over there. Now try to ask the question, according to classical general relativity, in what direction does the gravitational field point? Does it point towards there, or does it point towards there? The hopefully obvious answer should be that there's a 50% amplitude that it points there, and a 50% amplitude that it points there. But what that means is that space-time itself needs to be quantized. We need to have a wave function of the whole universe, a wave function of the dynamical properties, the curvature of space-time itself. That is what we seek in a quantum theory of gravity, and we don't have it right now. It turns out, of course, that we have a set of cookbook procedures for taking a classical theory and quantizing it. The real world, we think, is quantum mechanical. It's not really classical, and quantum mechanics is something we add on top. It's really quantum mechanical, and classical mechanics, a la Isaac Newton, is something that is a limit, an approximation to the true quantum mechanical reality that works very well when objects are really, really big. When you're working with individual atoms or electrons, quantum mechanics is absolutely necessary, but when you're working with big objects like the Earth or the Sun or even you and me, classical mechanics is perfectly fine. So there's no reason ahead of time that the way to find the correct quantum mechanical theory of reality starts by taking a classical theory and then quantizing it. But nevertheless, it turns out to work awfully well in many different circumstances. The most successful theory that we have within the realm of quantum field theory is quantum electrodynamics, QED. This is what won Nobel Prizes for people like Julian Schwinger and Richard Feynman. It is the quantum theory of electrons interacting with photons, and it works extremely well. But we have a classical theory of electromagnetism that also works extremely well. The way to get quantum electrodynamics is to quantize classical electrodynamics. When you try to take that cookbook and apply it to general relativity, it works at first, and then it breaks down. So it's not as if we don't understand anything at all about quantum gravity. We can take the first few steps. For example, you can consider gravitational fields that are weak, space-time that is almost flat everywhere, but tiny ripples on top of it. As a matter of fact, in most of the observable universe, the gravitational fields are actually pretty weak, so this is a very good approximation to many circumstances. We can quantize weak gravitational fields very easily. We get a theory of gravitons. We get a theory of particles that are quantized excitations of the gravitational field in exactly the same way that when we quantize electromagnetism, we get a theory of photons, the quantized excitations of the electromagnetic field. So the theory of gravitons works pretty well. It makes sense. We can scatter gravitons off each other. But then we try to push this theory a little bit harder. We say, what about when the fields aren't weak? What about what happens at very, very small distances? And there it breaks down. What we have are two kinds of problems. We have technical problems. We also have conceptual problems. The conceptual problems are that if you have a background space-time on which there are fluctuations in the gravitational field, you can quantize those fluctuations and the background space-time is still more or less classical. But if you want to truly quantize space-time itself, there become questions of what are we doing? In ordinary quantum mechanics, for example, the wave function depends on time. You tell me what time it is, I solve Schrödinger's equation, I tell you what the wave function is. But now, in general relativity, time isn't out there in absolute. It's not a background in which we move, it's part of space-time. It's part of the thing we're quantizing itself. So should the wave function depend on time? It's more likely that somehow time emerges out of the correct understanding of quantum gravity. But even though I can say all those words, I don't know how it actually works. This is one of the things that we're trying to address, one of the obstacles we have right now into making quantum gravity into a sensible theory. But even without those conceptual problems, we have technical problems. That is to say, we try to do what we think we know how to do, and we run into nonsense. There's a famous thing that often happens in attempts to quantize field theories, which is you get infinitely big answers. You can take two particles, you can scatter them, and you can ask, according to the rules of quantum field theory, how likely is it that these particles actually hit each other and bump off? If your field theory is well behaved, like quantum electrodynamics is, you get a finite answer. There might be steps along the way in which it looks infinite, but at the end of the day, you get a very well behaved finite thing. For some theories, that doesn't happen. For some theories, your first approximation to the answer makes perfect sense. Your second approximation is infinity. Things break down and there's no known way to fix them. Usually in nature, when this happens, these infinities are a sign that new physics is kicking in that you don't understand. For example, Enrico Fermi's original theory of the weak interactions had this property. The first approximation worked well, the second approximation was infinite. That was a problem. But now that we understand W and Z bosons, now that we understand the correct theory of the weak interaction, that problem has gone away. So this problem exists with gravity. When you scatter two gravitons off each other and look closely at what the answer is supposed to be, it looks infinite. We therefore suspect that there is new physics kicking in, the equivalent of W and Z bosons, but for gravity. That is the kind of thing that string theory purports to offer us, the new physics that makes everything suddenly make sense and gives finite answers. So string theory is just the idea that everything is made of incredibly tiny loops of string. If you were able to zoom in with a super powerful microscope on what was going on at very, very small length scales, you'd be able to resolve individual things that you thought were particles into vibrating loops of string. The reason you're not able to do that is because the loops of string are extremely, extremely small. They are approximately at the size of the Planck length, a length that was invented by German physicist Max Planck to describe the scale at which quantum gravity begins to become important. In numbers, it's about 10 to the minus 33 centimeters across. That sounds like a very small number, and it is. In fact, we can compare it to the size of a proton. A proton, made of 3 quarks held together by gluons, is small. It's smaller than an atom by quite a factor, but it's still about 10 to the minus 13 centimeters across. In other words, the Planck scale is 20 orders of magnitude smaller than a proton. It's a much tinier length than any of our current particle accelerators are giving us access to. So if you look at these tiny vibrating loops of string, you will see them as particles. They look particle-like to us because we can't resolve the fact that they're little one-dimensional loops of string. So when we talk about what string theory predicts, we will still be talking as if it predicts different kinds of particles. There will still be photons that are particles, etc. But they will really be different vibrational modes of the string. That is the idea behind how string theory is able to give rise to all sorts of different kinds of particles. It's not that the stringy stuff is made of different kinds of stuff for different kinds of particles. There is just one essence of string stuff that is the same for everything. But the little loop of string can vibrate in different ways, and the different modes of vibration correspond to bosons, fermions, what have you. Interestingly, there aren't that many ways to start with a vibrating string and get a consistent theory. In fact, since the 1980s, when string theory first became very popular, it was thought that there are only 5 possible ways to start with a little vibrating loop of string and get one consistent theory. These days, as we'll talk about briefly, we think that there's only one way to do it. Not that we've said that the other ways are inconsistent, but we found that what we thought were 5 different string theories are actually just 5 different versions of the same underlying theory called M theory. So this is part of the charm of string theory, that you start with an incredibly simple idea. There's just a loop of stuff, and you quantize it. How simple could that be? There's really nothing else there. I'm not leaving out any hidden assumptions. And you find a unique theory somehow. You find particle physics, gravity, everything you want to find just out of that little loop of string. So, in actually connecting it to the world, we try to make predictions. We try to say, how do we relate string theory to particle physics? Well, the first thing, of course, is gravity. The reason why string theory was invented in the first place was as a theory of the strong interactions. In the late 1960s, the early 1970s, we didn't yet put together what we now call QCD, quantum chromodynamics, the correct theory of quarks with different colors held together by gluons. We were still in the late 60s guessing at what the correct theory of the strong interactions really was. So one person noticed that if you look at all the different particles that seem to be relevant to the strong interactions, they arrange themselves with their masses and their spins as if they were little vibrating loops of string. And string theory was born as an attempt to explain the strong interactions. But it didn't work, and one of the reasons why it didn't work is because it kept predicting a massless spin-2 boson that coupled to every form of energy and momentum. In other words, string theory kept predicting a graviton and therefore be a theory of gravity. Even though you didn't want gravity, it kept appearing. So this is kind of a miraculous thing. Ordinarily, when we try to quantize gravity, we run into trouble. We run into infinities or conceptual problems or whatever. String theory is an example of a model where you didn't want gravity. You were trying to explain how protons hang together, and you kept predicting gravity. It turns out that not only do you predict a quantum theory of gravity, but it's a well-behaved theory. One way of thinking about why you get these infinite answers in ordinary attempts to quantize gravity is because the Feynman diagrams become exceptionally complicated. Feynman diagrams describe the different ways that particles can come together and interact, but to a particle physicist, each one of them gets attached to a number. And you can get complicated loops inside the Feynman diagram, and as those loops become small, the number attached to the diagram can become very large, possibly infinite. What happens in string theory is that you replace the Feynman diagrams with just lines connected to each other with the paths of strings through space-time. So they look like two-dimensional sheets. You have a one-dimensional string moving through time. It describes a two-dimensional sheet moving through space-time, which could describe a single particle splitting into two, for example. The number of possible diagrams you can draw describing such strings is, number one, much smaller than the number of Feynman diagrams that you can draw, and number two, much simpler. It turns out that what string theory does is to smooth off the sharp corners that would be there in the Feynman diagrams of ordinary quantum gravity, and you begin to get finite answers. Even better, you get more than a theory of quantum gravity. You get possibly a theory of everything. Different ways that strings can vibrate give rise to gravitons, but also to photons, also to gluons, to electrons and quarks. All the kinds of particles we know about in the standard model can be reproduced by vibrating strings. That's the good news. The bad news is that to actually reproduce them specifically turns out to be very, very hard. It turns out to be very difficult to go from what we think is the unique theory of string theory to the world in which we live. That's not really surprising because in one sense, gravity is very weak. Quantum gravity is something that is very far away from our experimental reach. We don't have a lot of explicit clues about how gravity and particle physics get together. We're left with only our IQ points, and sometimes they're good enough, sometimes they're not up to the job. So what we're trying to do is to get string theory, match it to the real world, so we ask, what predictions does string theory really make? The one prediction that string theory makes more strongly than anything else is that space-time is 10-dimensional. Strings want to propagate in a space which is 9-dimensional and 1 dimension of time. The bad thing about that is that it's not the real world. But at least the good thing is that it is a prediction of something, and the question is it possible to reconcile 10-dimensional space-time with the 4 dimensions that we see? The answer there is actually yes. It's been known for a long time how to go from a higher dimensional space to a lower dimensional space. If it had been the other way around, if string theory only worked in a 2-dimensional space-time, we would truly be in trouble. But it's easy to get rid of extra dimensions of space-time. String theory predicts that there are 6 dimensions of space that we don't see. The way to get rid of them is to curl them up. This is an idea that goes all the way back to Kaluza and Klein soon after Einstein invented general relativity. They said that if there are dimensions of space-time that are dynamical and curved, maybe there are ones that we don't see because they're curled up into tiny little circles or tiny little spheres. So string theory takes this idea and tries to take advantage of it. It says maybe these extra dimensions that we don't see really are there, but they're curled up into little balls the size of the Planck scale. That's the good news. And furthermore, the different ways in which you can compactify those extra dimensions tell us what the particle physics will look like at low energies. In other words, if string theory is right, the reason why, for example, we have 3 families of fermions in the Standard Model turns out to be a particular topological fact about the space on which we've compactified the extra dimensions. We've turned a statement about the number of particles we see into a geometrical statement about extra dimensions that we don't see. That's interesting because it offers a new way to solve the kinds of problems we were stuck with. Why are all these particles there? The bad news is that there are too many ways to curl up the extra dimensions. The ways that we have to curl them up are not unique. From the mid-1980s, when string theory first became popular, to the late 1990s, people were crossing their fingers and hoping that somehow there would be one way to compactify that was the best. So people were trying to look for that, and what they found is that with different model compactifications, they could get all sorts of different possibilities. For example, supersymmetry is a robust prediction of string theory as well. That's good news for our thinking about dark matter, because our favorite theory for what the dark matter might be is the lightest supersymmetric particle. But then it turns out that string theory also predicts that there should be axions. It also predicts that neutrinos should have mass. So far, string theory is predicting too many things. It's not picking out one candidate for dark matter as the right one. Things got slightly worse in the 1990s when it was realized that string theory is not just a theory of strings. Remember that one of the virtues of string theory is that it's unique. You start at a particular place and you derive things that are necessary. You can't get around them. The non-uniqueness comes when you go from a large 10-dimensional world and compactify. There are many, many ways to do that. But in the original 10-dimensional description, things are very unique. So people realized that in that unique description there lived not only one-dimensional loops of string, but higher dimensional objects known as branes. The word brane comes from the word membrane, which means a 2-dimensional thing. If you live in 3 spatial dimensions, the only things you can really easily imagine are 0-dimensional particles, 1-dimensional strings, and 2-dimensional branes. But if you have 10 dimensions or 9 dimensions of space to play with, then you can imagine 3 branes, 4 branes, 5 branes that are 3-dimensional, 4-dimensional, 5-dimensional, etc. So it was discovered in the 1990s that all of these do play a role in string theory. There are different kinds of branes. Some of them have miraculous properties. Some of the miraculous properties are that there can be particles, strings, fields, that are confined to the brane. In other words, you could have a brane living in some higher dimensional space, But all of the electrons and photons of this particular construction were stuck on the brane. They can't escape out into the extra dimensions. So if you were made of those particles stuck on the brane, you wouldn't be able to tell that there were any extra dimensions. The interesting thing about this is that it makes the problem of non-unique compactifications worse. Now, not only do you have many different geometrical ways to curl up the extra dimensions, but within those curled up extra dimensions, you can start putting in branes. You can start saying maybe we live on some of those branes. So we're faced now with a bit of a conundrum. Starting from a set of unique ideas in 10 dimensions, we have a multiplicity of ways of getting down to 4 dimensions. The best estimates that we have right now are something like 10 to the 500 different possible ways to go from 10 dimensions down to 4 in an interesting way. By interesting, we mean a way that doesn't dissolve away very quickly. A potential place that you could imagine living in the universe of string theory. That's the bad news. We don't like it when we lose uniqueness somehow. We're still struggling to somehow find our way through those 10 to the 500 different possibilities. The good news, though, is that some of those possibilities are experimentally testable. We don't know whether or not we're going to be lucky enough to be involved with one of the testable ones, but the point is that there are new ways that we've realized for new dimensions of space to manifest themselves in experiments. In the old days, in the days of Kaluza and Klein, when they first suggested that there are curled up extra dimensions, all they did was just curl them up so small that you couldn't see them, by which we mean no experiment that had been done then could possibly reach them. And of course, since we haven't directly seen evidence for them, we still do the same thing today. But now, when you have branes, a new possibility opens up. What if we really are living on some 3-dimensional brane, confined in some bigger space? Remember, when we say that space is 3-dimensional, we mean when we do experiments, we only perceive 3 dimensions. For example, if you take a stick, you can take a second stick and you can tie them so that they are perpendicular to each other. Then you can take a third stick and you can tie that third stick so it is perpendicular to the first 2. That means there are at least 3 dimensions of space macroscopically. But try as you will, you cannot take a 4th stick and tie it so that it is perpendicular to all of the previous 3 all at once. It can't be done. That is an experimental demonstration that we only have 3 dimensions of macroscopic space. However, what if there are more dimensions but we just can't get there? Then the problem becomes much harder. We could have large extra dimensions and just not notice them yet. The real issue of large extra dimensions is that even though you can confine the particles of the standard model of particle physics to a 3-dimensional brane, there's one particle you cannot confine, and that's the graviton. Remember, gravity is a feature of space-time itself. Gravity is the curvature of space-time. So if you have some object in a set of dimensions, it's going to have a gravitational field that stretches out into all the dimensions, not just on the brane. And how do we know how many dimensions gravity feels? Well, we have Newton's law of gravity. We have Isaac Newton's inverse square law that says 2 objects pull on each other with a gravitational force that is inversely proportional to the square of the distance. The reason why it's the square of the distance, if you can imagine the gravitational force lines coming from one object, they fade away as 1 over the distance squared because the area they're covering goes up as the distance squared. But that's only because we live in 3 spatial dimensions. If we lived in 4 spatial dimensions, the force between 2 particles due to gravity would go like 1 over the distance cubed. If we lived in 5 spatial dimensions, it would go like 1 over the distance to the 4th, and so forth. So if we lived on a brane where the particles of the standard model were confined but gravity leaked out, Isaac Newton's law of gravity wouldn't be right. We wouldn't have an inverse square law. We would have an inverse cubed law or inverse fourth law or something like that. So the clever suggestion was made in the late 1990s that maybe we do have an inverse cubed law, but only on really, really tiny length scales. But by really, really tiny, I don't mean the size of a proton, I mean a millimeter across. So macroscopic length scales, but length scales where we had not yet done experiments. So people started doing experiments. They tried to test Newton's inverse square law of gravity on very, very small distances by taking one heavy plate and bringing it very, very close to another heavy plate. They were able to squeeze the experimental limit on the size of extra dimensions down from 1 millimeter to 1/10 of a millimeter. So that's a whole order of magnitude. That's a lot of progress. But still, it is very plausible to us today that there are extra dimensions of space 1/10 of a millimeter across. We just haven't noticed it yet. So we need to push forward with this kind of idea. We can't get rid of the fact that there should be a quantum theory of gravity. We have quantum mechanics, we have gravity, we have to get them together. Especially as cosmologists, we care about things like, where did the universe come from? Where did the fluctuations come from that we think are due to inflation? Our explanation for those fluctuations using inflation said that you have quantum mechanical fluctuations in the early universe during inflation, giving rise to density perturbations, and therefore we later measure the gravitational fields of those density perturbations. In other words, the inflationary scenario for explaining the observed density fluctuations in the universe involves quantum gravity in an intimate way. If we want to claim to understand those things, we're going to need to understand quantum gravity. What we really care about, of course, is dark matter and dark energy. So in the next lecture, we're going to talk about how to take string theory with all of its extra dimensions and all of its different possibilities and tease out implications for what the vacuum energy might be. There might also be implications for what the dark matter particle is, but right now that's much harder to get. When it comes to vacuum energy, string theory offers a very provocative, perhaps scary, perhaps even crazy, but at the very least interesting scenario for why the vacuum energy of the universe might be the dark energy we observe.